Yeah, comes on everyone. Let's start off. The last thing that we did was this thing, recoil velocity. So let's go ahead. Are those cams on? Collisions. So how do you define a collision? So a collision is a process in which momentum and energy are transferred in a very short amount of time. Right? And the forces involved during the collision, since the time is small and you want to give a finite momentum, what is momentum? Force into time. So the forces involved during collision are very large. And they act for a very small time. So, and these forces are called impulsive forces. So, impulsive forces are those which are very large forces, but they act for very small time. So, when you jump from, let's say, first floor and you break your leg, what is breaking your leg is not the weight. Your leg hits the ground and stops in a very short time. So, it generates a huge impulsive force that creates the fracture. When you're hitting your friend, what hurts is not the weight of your, hand. The punch when you're hitting, all that momentum suddenly stops. It generates a large force, as an impulsive force. These forces are called impulsive forces. So if you try to plot this thing, force versus time graph, they will just bump up peak value and then become constant like this. So this will be a very small time interval. Right? And this area under this FT graph will be integral FDT. This is nothing but the change in momentum. So force is large, time is small, but the area is a finite value, right? And this is given by J. So J bar is a symbol. This is your linear impulse. Now don't get confused. Impulse and impulsive forces are two different things. Linear impulse with a simply change in linear momentum. So what are impulsive forces? Large forces which act for small time are called impulsive forces. What is an impulse? Impulse is simply a change in momentum. If a body ka momentum changes, we say there is an impulse. There is an impulse. Clear with this? So, so how do you know whether a force is impulsive or non-impulsive? Let me show you an example. And why is this important? The classification is important. Let's say we got a block of mass m here. The ground is rough. And let's say a bullet of mass small m comes and hits the block. Now, if I draw the FBD of the block and the bullet during collision, look at the forces. So when the bullet hits the block, you have a normal reaction. Newton's third law, the bullet also will experience that force N. So this force between the bullet and the block is very large and acts for a short time. And this block will have its own weight, mg. Then we have a normal reaction on the ground, ng. And we have friction which will act backward. Now look at this. Any force that is involved during a collision is an impulsive force. When the bullet hits the block, the forces generated are very large. So these are impulsive forces. So N is impulsive. What about mg? Mg does not change. Mg is constant with time. And what is n ground? N ground is also equal to mg. So n ground is also an impulsive. What is friction? Friction is mu into n. So all these are non-impulsive forces. But same thing, let me show you a different picture. You keep the block on a rough ground, and let's say this time the bullet is hitting at an angle like this, at an angle theta. Now, if you try to draw the forces, this bullet will push n like this. You will push the bullet back with n, right? And if I take this angle to be theta, your mg is there. Mg is never an impulsive force. Mg is always constant, right? But now your n ground becomes impulsive. Why? What is n ground? N ground is mg plus n cos theta. So if you add a large force to a small force, it still becomes large, right? And what about friction? Friction depends on ng, so friction also becomes impulsive. So now n ground and friction are impulsive. So during collision, whatever forces you get, if they interfere with other forces, they will also become impulsive. Mg is always non-impulsive. Did you see in both the questions, even though the forces and the picture is there, just making it an angle, it changed the whole thing. So Mg is still non-impulsive. So during collision, that N is big. Because of that, the ground force also becomes very big. And because of that, friction also can become very big. Clear? Shrihar, you have to switch on your cam when you join the meeting, right? So I don't know what is a doubt there. So focus on the class. All clear with this? Clear with this? Let me take one more example. So we got a ball here of mass m. Same thing. Let's say bullet comes and hits the thing horizontally. Let's say in the second case, the bullet comes and hits the thing vertically like this. So now if I try to draw the forces, can you tell me which forces will be impulsive and non-impulsive? Friction is impulsive because what is F? F is equal to mu ng, isn't it? So friction depends on impulsive force. So friction also ka value will be big, right? So here again, if you draw the FBD, what are the forces on the block? We have tension, we have mg, right? And you're colliding here, so this will be N. So here N is impulsive. Tension and mg are non-impulsive. But in this scenario, we have tension. This becomes n cos theta, right? So whatever then is acting here, and this is mg. So tension becomes mg plus n cos theta. So tension also becomes impulsive. So that means when the string suddenly becomes tight, right, it feels like a jerk. Yeah, both. Right, Aditi. So T and N are impulsive. Mg is non-impulsive. So Mg will never be an impulsive because the definition of impulsive force should be large for a small time. So what do you need this classification? So you need to understand something. If there are impulsive forces involved in the problem, you cannot conserve linear momentum. Because see, because these forces are so large, they actually start affecting the momentum. You cannot conserve it. But if you have non-impulsive forces, you can actually conserve momentum. Approximately it works. So momentum cannot be conserved because even the time acting is small, since the forces are large, they do create a finite momentum. Cannot be conserved if forces are impulsive. If non-impulsive forces are present, theoretically, even then you can't conserve. There'll be a small error, but it's an decent, matlab, that much you can say. If non-impulsive forces are present like mg, momentum just before and momentum just after can be approximately conserved. Because, for example, you take mg into time, mg is finite and time is so small, dt tends to 0, the whole value will tend to 0. Before and after collision can be conserved. And if you remember this problem here, it thing exploded into two pieces and they started flying back. In this question, if you see, when the explosion is happening, there is an mg acting on the body. But we conserved momentum, right? Technically speaking, when there is an external force, you can't conserve the momentum. So we actually ignore the mg. This is what I wrote. We can neglect mg during the expansion, explosion, during the time interval is very small. Because mg is a non-impulsive force. Clear with this? So when you have non-impulsive forces, momentum can be conserved just before and after. Because the time interval is very, very small. It works out. So I hope everyone got an idea what is impulsive, what is non-impulsive force. Now let me show you how they can frame a question. You get some really good ones on this, and this concept is important, impulses. You will see this thing again in collisions later on, and again you'll see this in rotation. So let's say we have a block. Mass m. A bullet comes at an angle, hits the block at an angle theta, mass m, and the speed is u. The floor is smooth. In the second case, same thing, but this time the floor is rough. So the bullet hits the block and gets stuck. Right? And assume the block is always in contact with the ground. The bullet hits the block. as shown and gets stuck inside it, gets embedded. Assume the block does not lose contact with the floor. There is a possibility if you hit right, there is a chance this block also can fly off. We'll not get into all that. Block remains in contact with the floor. Find the velocity of the system after collision. The B is a very important one. Let's see. How will you do this? First was easy. Try. I'll give you a minute for the first one, 1 or 2 minutes. Right, Srihari. Right, Ovia. Nee, Utsa, that is wrong. Right, Arya. Let's see. The first was straightforward. Always, if you look at the forces, so if you look at the forces involved during the collision, this is N, impulsive, right? Then we have N ground, non-impulsive. No, that is also impulsive. Mg. So this actually also becomes impulsive because of that N. But there is no friction, so there's no problem. So here, what is my system? Always define your system properly. Here, my system is bullet plus block. So if you take my system as bullet plus block, that N becomes an internal force. And you can clearly see horizontally there are no forces. So after collision, the bullets get stuck. And it is given in the question, it will not lose contact. That means there is no vertical component of velocity, but the system is horizontally moving. Now, how did that happen? Don't worry about it. The ground is taken care of. So your system is bullet plus block. Since there are no horizontal forces, horizontal momentum is conserved. Vertical momentum is not conserved. So what is the horizontal momentum? So you can divide this component to velocities. This will be u sine theta. This will be u cos theta. So mu sine theta is equal to m plus m vx. There, you got it. Mu sine theta by m plus m. Now here they can ask you one more question. Find the impulse due to the ground. I didn't ask you that, but if they ask you what is impulse due to the ground, sometimes they'll get questions like this. So what is impulse due to the ground? Basically, you're asking change in momentum in the vertical direction. So this is the delta p in the y direction. So what is the final momentum? That was 0. What is the initial momentum? M into u cos theta. there. Sometimes if you ask you the questions like this, they're indirectly asking you find the change in momentum in that direction. So impulse due to the ground, or this is also impulse due to the n ground. So mathematically, if you want to write, this thing is written as integral ng dt. Clear with that? This is minus of minus mu cos theta. Sometimes you get questions like this also. Find the impulse due to the normal reaction on the ground. Find the impulse due to the none between them, something of that sort. So indirectly is asking to find the change in momentum in that direction. What about the second one? Now for the second one, when I draw the same picture, you will notice something. This n is impulsive, fair enough. Because of that, n ground becomes impulsive. Because of that, friction also becomes impulsive. Now I can't conserve horizontal momentum, right? So horizontal momentum is gone. So let me draw the picture. So listen how to handle these kind of problems. Huh? This is important. We will see this again a few more times. So this is before collision. This is your bullet. This is your theta. This is mass small m. So horizontally, the velocity will be u sine theta. Vertically, the velocity is u cos theta. Okay. So during collision, what will happen? What will be the forces acting on the block during collision? During collision, the bullet is getting stuck inside. It's going inside. So because of which you get a force here, let's call it n dash, and this force will be n dash, which is an impulsive. Because of this, n ground becomes impulsive, because this friction becomes impulsive. And finally, after the collision gets over and the bullet gets stuck, the bullet is stuck inside. Since the block is in contact with the ground, Vy will be 0, and this will start sliding with Vx. This is just after the collision. After this, because of the friction, it will slide and slow down, will not get there. So this is a just after collision. So just after, and the time interval is very small. From here to here, it will take dt, very small time interval. So here, the time will be almost negligible. You're talking something like a millisecond or something. Now let's look at the problems you are facing here. So the first problem here, friction is impulsive. Why? Because n ground is impulsive. Why n ground is impulsive? Because this n cos theta is making it impulsive. So this n becomes n dash cos theta plus mg. That's why it became impulsive. And friction became impulsive because of this. So friction is impulsive. And so if you're impulsive, you can't conserve linear momentum, right? Horizontal momentum is not conserved. Vertical, though, anyway, you can't conserve because of that n ground. Second thing, the bullet is getting stuck. Now, later on, we will talk about this. It's called an inelastic collision. When the bullets get stuck, matlab, it is getting deformed, it is doing something. There is a loss of energy. Bullet is stuck to the block. So there will be an energy loss. Means you can't conserve energy also. There, you lost both your conservations. You can't conserve momentum, you can't conserve energy. Clear so far? So how do we handle this? So listen carefully. Let's look at the momentum in the vertical and the horizontal direction. In the vertical direction, What are the forces? mg we are ignoring, so integral n dt will be change in momentum in the y direction. We ignore mg because n is much greater than mg. Technically, I should have written n minus mg into dt and all that stuff, but we are ignoring it. What we can't do here? Right. So again, what is my system here? Remember, my system is bullet plus block. Conserve energy because it is getting stuck, right? If the bullet is getting stuck, matlab there'll be some deformation, there'll be heat produced and all that stuff. It's pushing the material and going inside and getting stuck. So it gets hot and everything. It's called an elastic collision. We will talk about that today, it'll come. But you must have heard about an elastic collision. So energies are not conserved when they get stuck. Primarily because of deformation. One other thing. So integral n dt will be P vertical minus P final minus P initial. So remember, my system here is bullet plus block. Finally, the block and the system is not going up and down, so that is 0. Initially, it is going minus of minus mu cos theta. There, this is your impulse. Integral n dt. Again, don't worry about the integral sign. We're not going to integrate anything. Integral n dt is mu cos theta. So just understand the meaning of it. This is the impulse due to normal. What is impulse? Change in momentum. So this is a change in momentum because of the normal reaction on the ground. That is how you can read it as. This is impulse due to normal. Perfect. This is the vertical thing. Now in the horizontal direction, what is the force acting in the system horizontally? Friction. Which way? Backward. So minus integral friction dt. This will be change in momentum in the horizontal direction. The final momentum, the bullet and the block are going to the right side, which is m plus mvx. Minus, initially the bullet is going with mu sine theta. So this will be integral f dt is equal to mu sine theta minus m plus mvx. Right? Now, since when the block hits this thing, the block will start sliding, the friction will be maximum. Because the moment the block and the system will get some velocity, it will start sliding here. So let's take that case. So if we consider f is maximum, you will see why it is. There will be a trap there. Basically, this will become integral f max dt. But what is f max? Integral mu n dt. This is mu sine theta minus m plus mvx. But what is n dt? N dt is mu cos theta. Substitute here. You end up with mu into mu cos theta. You'll get mu sine theta minus m plus mvx. So we get vx is equal to mu cos theta sine theta minus mu cos theta by m plus m. There, that's your final answer. That is the velocity of the bullet and the block when they get stuck. So we didn't use momentum conservation, we didn't use energy conservation, we did something else. This is actually Newton's second law. Force into time is change in momentum. See again what we did. We took the vertical direction. From there, the only vertical force acting is n. We ignored mg. So n dt will give you change in momentum in vertical direction. Horizontally, there's only one force, friction. Friction into dt will give you change in horizontal momentum. And if you take f is maximum, we'll get f max is mu n dt. So eliminate n dt will go off, and then you'll end up with vx. Have a look at this. But there is a problem here. We'll see that, but first understand this. Some people figure out this also. Then there is a trap. So what is a trap? Any doubts on this page? Any equation that you're not clear, please ask. So let's see your velocity Vx, which is mu sine theta minus mu cos theta by m plus m. The answer is great. So this is valid if Vx is greater than 0. So if you got Vx is positive, let's say if they give numbers, if you get Vx greater than 0, it is great. Just try to understand, what if Vx you get negative? What is the meaning of that? If Vx is negative, you know what you're telling? The bullet is hitting the block like this and the block goes backward. Does it even make sense? You're getting the problem? If Vx becomes negative, means what? The block is not going front, it is coming back. So something went wrong. So what do you mean by that? So let's see that. So sine theta minus mu cos theta must be greater than or equal to 0. So this answer is valid as long as mu is less than or equal to tan theta. So this is the problem. So after solving, so after whenever you get questions like this, you always have to check once more. After solving, if you get Vx less than 0, this implies, so we did a mistake there. The friction is not maximum. Tell me one thing, what is the job of friction? Is the job of friction is to apply maximum force? No, right? That means when this bullet was hitting the block, the forces generated are not that strong. The friction need not give the maximum value. Are you getting it? What the mistake we did is we assumed F is maximum. For example, think of like this. When the bullet is hitting the block, and let's say the force applied is 1000 newtons horizontally, and let's say your F max is 3000. Now you tell me, if the bullet is pushing with 1000 newtons and friction can give 3000 newtons, how much will the friction give? 1000 newtons, right? Are you getting the catch there? That means the block won't even move there. So the mistake we did, we assumed here F is maximum. So F will be maximum only if the block moves. So there is another possibility, right? The friction is not a maximum. That is, the forces during collision are unable to move the block. And you can think about it why. Look at this. What if I shoot the bullet like this, a very steep angle? If you shoot like this, won't NK value become very big and horizontal component become very small? So you don't have enough horizontal force to push the block anymore. So the forces during collision are less than F max. Getting it? So therefore, F is not equal to mu n anymore. You can't write this. F is not equal to mu n, right? F is less than mu n basically. So that second equation goes wrong. This equation you can't write in. You can't solve this question basically with that data. But you know something else. That means the block is not moving, right? That's why F is not maximum. The block does not move. Perfect. If the block does not move, therefore Vx is 0. So this answer is valid only if Vx is positive. If you got Vx negative, that means the block didn't move, so the answer is 0. Are you clear? Negative values are not acceptable. So the answer will come out like this. So Vx will be mu sine theta minus mu cos theta by m plus m. This is valid when mu is less than or equal to tan theta. 0 if mu is greater than tan theta. Basically angle of repose. So whether the block will move, the final answer will depend on mu ka value. Are you clear what we're doing there? There is a possibility, think about that. The friction is so strong, it didn't let the block move only. The bullet just got stuck and just everything is at rest. So that depends on mu ka value there or the theta ka value. If mu is given, then you can get from theta. Are you clear how we did do this? This is unlike any other problem we did before. This thing, if you see now, this is not pure FBD thing. This is not energy conservation. This is like a third technique. It's like a form of a second law, basically. We are just using impulses there. Pretty good problem. You should definitely check it out. Next class, we'll do one more like this. And rotation, we will do one more deadly one than this. But this will be a good paragraph questions. Clear. These are impulse-based questions. One of the most common mistake, right? People, that is not the final answer, basically. There is a possibility the block doesn't. All clear with this? Any doubts? Vedika? Clear with this? Sudiksha? Uh, yeah, do adjust your cam? I can't see you, Sudiksha. Shaunak, adjust your cam. Can't see you. Advait can't see you. Utsa, adjust your cam a bit. Great. Next thing. So let's go to the collisions. Now in collisions, we have two types, head-on and oblique. So what's a head-on collision? So head-on collision, right? The velocities of the bodies are along the common normal. The velocities of the bodies are along common normal. They're said to be a head-on collision. What is again common normal? We have done this in NLM also. If you have two spheres, the common normal will be line joining the centers. So if the velocities are like this, it's a head-on collision. Suppose if you have an incline like this is a common normal. So if the velocity is along the normal, then it's a head-on collision. So these are head-on collisions. What is an oblique collision? If velocities are not along the common normal. So if your head-on collisions is good, oblique collisions is easy. So we will focus on head-on anyways. Example, same thing. This is your common normal. But this guy is going like this and this guy is going like this. They are moving at angles. Or we have a floor like this and the ball comes and hits at an angle and bounces off like this. This is also oblique. Best example, if you're playing carom board, right? You must have seen this. In caroms, now let's say we have that thing here, and let's say we have a coin here. And when you're with a striker, when you're hitting this, we say, no, this is a sure shot coin. Heard this thing? So the sure coin is your head-on collision. You heard that word? This is a sure coin. Basically, it's a head-on. Or if you ever played the other one, cut shot. We have the coin, and you're hitting this with a striker at an angle. So this thing will come and hit somewhere here. And after hitting here, this will go into the hole like this, the cut shot. And after this striker will bounce off in some other direction. So cut shots are oblique collision. So that's the easy way to understand what is an oblique and head-on collision. Clear? Hope everyone has played carom board, so All clear with this. The definition of an oblique and a head-on collision. Clear, Shma? Ishman, clear? Yeah. Now, the next thing. This is important, everyone. Listen. So, what happens exactly during the collision? This process is important. Shrihari, you can say like that. So, listen to this thing. Let's say we have two spheres or two balls or whatever. M1, M2. Let this go with U1. Let this go with U2. And U1 is greater than U2. So, the ball from behind will come and hit M2. And now, because the U1 ka speed is more, when they collide, what will happen? At the surface of contact, there'll be slight deformation. The body gets deformed. Remember, we are not studying for rigid bodies. Rigid bodies don't undergo this kind of collisions. Anyway, rigid bodies are hypothetical. So the two bodies will start colliding. So they start pushing each other, kind of like a spring. So we get a normal reaction here, we get a normal reaction here. Because of this, what will happen? The speeds will start changing. So here, the deformation between them behaves like a spring. Not a perfect spring, but yeah, it does play the role of a spring. So the deformation of the bodies plays the role of the spring. And that's what happens, right? When your car goes and hits something, you get a dent. And because of this, what will happen? The speed V1 will start decreasing and speed V2 will start increasing. But remember, still V1 is greater than V2. Suddenly, speed can't change. And then, so the deformation won't stop. The body will continue to deform. The deformation will increase. They will start getting stuck more and more. V1 and V2. At this point, V1 becomes equal to V2. This becomes your maximum deformation. And you lose a maximum amount of energy here. So if you look at this thing now, this guy is looking like remember this thing? State 1, state 2, state 3. Doesn't it look like this case? It kind of looks like this. If you just imagine the deformation as a spring, this is what is happening 1, 2, 3 case. Then what happens? Now there are three possibilities that can happen. Case 1, the bodies will get stuck to each other permanently. So if these are plastic bodies, now what will happen from here will depend on the type of bodies. For example, if you take chapati ka dough and hit a car, what will happen? It will get stuck. These kind of bodies are called plastic bodies. We'll talk about that. So this collision is called perfectly inelastic. So the bodies will be permanently stuck, something like this. So that there's a deformation will be there. And both of them will move with a common velocity. This is one possibility. Okay, this can happen, right? And this you'll have maximum loss of energy. So in perfectly inelastic collision, you get maximum loss of energy. This is what I was saying. Whenever bodies get stuck, you lose a lot of energy. Second possibility, you collide and the bodies will get separated. There'll be some deformation. Think of like this. You go with your cycle and hit the car in front of you. So, right? Or let's say your car goes and hits another car. What will happen? They will hit the front part and back part will get damaged, but they will separate out. So there will be still some deformation left out, but the bodies got separated. Meaning, if you think in terms of the spring got pushed them away, but still some part of the spring is still compressed. V2 becomes greater than V1. They separate. They go separately. But still, there is some loss of energy. You still lost some energy. This can happen. This is what happens when your car hits something, you get a dent. There is some loss of energy. This is called partially elastic, or they'll simply use the word elastic collision. There's a third possibility. How do I draw this? the bodies will completely, the deformation completely comes up. The bodies become normal. This generally happens with your billiard balls. V1, V2, there is no deformation. You don't lose any energy. You recover everything. This is the most idealistic case. No deformation. In this case, energy is conserved. You don't lose any energy. This is called perfectly elastic. So there are three possibilities that can happen. So every collision, right? The story is same. Whenever two bodies collide, state 1, 2, 3 is compulsory. You can't avoid this. So this is state 1, state 2, and state 3. All will undergo state 3. After 3, what happens will depend on the type of the material. Clear with this. So after state 3, you can get any one of these three. So the problem is split into 3 parts. So who decides what will happen? I'll go back to that. So we define something called a plastic body. Again, plastic does not mean your chair ka plastic. So plastic bodies are, these bodies do not generate any internal restoring forces. We will talk about that in elasticity, but let's see. These bodies do not generate. That word is self-explanatory, internal. So these forces will internally should have occurred. Restoring. So these forces should try to bring you back to the normal state. That is, when the force is applied, body gets deformed. So chapati ka dough, you poke it, it will get deformed. But when you remove your finger, it doesn't come back to the normal state. It does not recover at all. Chapati ka dough is pretty close to a plastic body. So if I have to show you with a picture, let's say if you have a ball, someone applies a force F, the body becomes something like this. Then you remove the force. Body still remains the same. There is no recovery at all. These are plastic bodies. So if the bodies are plastic, this is what will happen. They will get stuck together and they'll go together as one part. The second type of bodies are called elastic bodies. So elastic bodies, these bodies deform when you apply force. So again, don't get confused between rigid body. Rigid body won't even deform in the first place. And rigid bodies are hypothetical. So these bodies deform when you apply the force. And they recover completely when the force is removed. Arya, keep your cam on. So if I have to show you on the picture, right? So yeah, memory foam pillow is a decent example. So force F. So this will get deformed. And when you remove the force, it again comes back to normal. But is this clear, everyone? What is happening during the collision? So no matter which collision it is, perfectly elastic collision, perfectly inelastic or anything, state 1, 2, 3 is common. After 3, what will happen will depend on the material. Got this? Now, in this thing, if you observe, the forces between them are always internal. So how do we solve these problems? Basically, whenever you solve collisions, there are only two concepts here. First thing, conservation of linear momentum. Since the forces involved are internal, momentum is always conserved in all collisions, all types. Meaning elastic, inelastic, this thing. It doesn't matter how much you get deformed, it won't matter. Conservation of linear momentum. So M1 U1 bar, M2 U2 bar is equal to M1 V1 bar plus M2 V2 bar. Second thing, now energy is not conserved, so we use something else. E is equal to coefficient of restitution. There, that's a new word completely. So restitution is a Latin word. What it tells is how much energy is recovered from deformation. It tells you how much did you get back. So when the bodies collide with each other, the energy will go into the deformation. In that, how much did you recover? How much energy is recovered from deformation? Think of like this. Let's say the bulk energy is 100. When they both collided, the bulk energy is 60, 40 went into deformation. After the collision got over, let's say still 10 is stuck inside, so 30 got recovered. So there's no guarantee every time it will be recovered everything. So this thing simply gives you how much energy is recovered from deformation. So how much you sent into deformation, how much you got it. So for E is equal to 0, this is for perfectly inelastic. There is no recovery at all. Whatever went into deformation, nothing came out. This is perfectly inelastic. For perfectly elastic, E is equal to 1. Everything is recovered. So E ka value will lie between 0 to 1. So the formula for this, E will be V2 bar minus V1 bar by U1 bar minus U2 bar. Magnitude. So this is the relative velocity of separation. So V2 minus V1 are the final velocities. Right, along the normal by relative velocity of approach. So U1 minus U2 is the initially with what velocity they're approaching. Along the normal. So V2 minus V1 bar can be written as E times of U1 minus U2 bar. So final relative velocity is E times initial relative velocity. Pretty useful thing. There. These are the two concepts you use to solve problems in collision. That's it. Momentum, restitution. Let me show an example how you can solve a question. But have a look at this. Yeah, Srihari did the same thing. So see, example, let me show you a question. Let's say we have a ball of mass 2m, and let's say we have a ball of mass m. This is coming with u, and let's say this is also coming with u. Let's make it 2u. And let's say E ka value is half. So how do you solve these questions? Step 1, draw the final diagram. Or assign final velocities. So I will assume the picture finally will look like this. So this is V1, and after collision, this is V2. I don't know. You can assume any direction. Science will take care of it. Step 2, conserve momentum. Step 3, use quotient or restitution. So conservation of momentum, this will be 2m into 2u. Right is positive, left is negative, minus mu. 2m v1 plus m v2. This will be 4 minus this 3mu. This will be 3u is equal to 2v1 plus v2. That's your equation 1. Quotient of restitution, E is equal to half. V2 is forward, V1 is also forward, U1. So understand this is my U1, this is my U2. So it is V2 minus V1 by U1 minus U2. So U1 is 2U, U2 is minus of minus U. Signs are important. This will be V2 minus V1 is equal to 3U by 2. There, 2 equations, 2 unknowns. Solve them, you'll get V1, V2. So you can take this and substitute there. How much will that be? So if you take this and substitute here, you will get 3u is equal to 2v1 plus v1 plus 3u by 2. That will become 3u by 2. So v1 will be u by 2. And v2 will become something mistake here. That is 3u now. v1 plus 3u by 2, 3v1. And then v2 will become 2u. That's your final answer. So after the collision, the 2m ball will go with u by 2 and the m ball will go with double the speed. All clear what we did? Momentum and restitution, that's it, 2 steps. Clear? Let's see a question on this. There, but what is happening during the collision? This thing is important. You should know what is happening there. Let's do this. Let's say this ball of mass 3m. This is going with u. This is a ball of mass m. This is also going with u. And let's say E is equal to F. Find the final velocities. Let's say we have ball mass m u1. Let's say another ball of mass u2. E is equal to 1 and u1 is greater than u2. Find the final velocities. U by 4, 5u by 4. Okay, looks right. So let's see. So after collision, let the velocities be v1, v2. Conservation of momentum, 3mu minus mu, 3m v1 plus m v2. We get 2u is 3v1 plus v2. Quotient of restitution, this is v2 minus v1. So this is my u1 and this is my u2. So u2 u1 minus u2. So that will be u minus of minus u. This is f. So v2 minus v1 will be u. So take this v2 and substitute here. 2u is 3v1. v2 will be v1 plus u. 4v1 is equal to u. v1 is equal to u by 4. And v2 will be 5u by 4. Make sense? Once you got the equations, it is just solving. What about the b part? B is the standard result. We will see. Right, Shaurya. Right over here. Yeah, Anita got it. One Shika got it. Samyak. Yeah, most of you got it. What about this thing? So in the B part, if this is M, this is going with U1, this is M, and this is going with U2. Finally, let the velocities be V1, let the velocities be V2, MU1 plus MU2, MV1 plus MV2. You get U1 plus U2 is V1 plus V2. E is equal to V2 minus V1 by U1 minus U2 is equal to 1. We get V2 minus V1 is equal to U1 minus U2. When you solve them, you will get a V1 will be U2 and V2 will be U1. Basically, the velocities get exchanged. Means after the collision, the picture will look like this. So this guy will go with U2 and this guy will go with U1. So there's an important thing there. If two bodies of same mass collide elastically in the head-on, they exchange velocities. So here E is equal to 1. Collide perfectly elastically. Every time they won't use the word perfectly, they'll simply say elastic. If it is not elastic, they'll give you the Eka value. So elastically, they exchange velocities along the common normal. This is a better word. Clear? So remember this result comes a lot. So just standard one. All clear with this? Take a break. Come back by 9:40. We'll continue from here. Any doubt so far? Sure. Come back in 5 minutes then. Hello, let's start off. So let's say we have a pendulum. This mass is 2m. This is fixed here. This is a string of length L. So here we have a ball of mass m. It's coming with speed u and collides with this. And let's say E is equal to half. So find u minimum so that the pendulum completes a vertical circle after the collision. So this ball will come and collide, and this 2m I wanted to go in a circle. Let's give it a try. चलो ओके अच्छा हुआ चलो ठीक है ठीक है ना चलेगा सर राय सर कंफर्म कर लेना चलेगा कल हम दोनों मैनेज कर लेंगे कुछ इतना बड़ा बात नहीं है ये सीनियर्स तो नहीं है ना सिर्फ जूनियर्स का बैच ही है चलेगा प्रॉब्लम नहीं है हाँ हाँ चलेगा ठीक हाँ प्रॉब्लम नहीं है ठीक So how do we do this thing? We combined vertical circular motion with the collision. Let's see. So this is how it goes. So this is your thing before the collision. So after the collision, 2m, let's say this is m, and let the speed be v1 and the speed be v2. So the story is still the same. Remember, tension is vertical, so there are no horizontal forces. Mu, 2m ka momentum is 0, mv1 plus 2m v2. U is equal to v1 plus 2v2. This is your first one. Next thing, restitution E is equal to V2 minus V1 by U1. So remember, this is your U1, that is U minus 0, and this is half. So from here, you get V2 minus V1 is equal to U by 2. What you want is V2, so you don't want V1. Just add equation 1 plus 2. If you add 1 plus 2, V1 will cancel. You end up with 3V2 is equal to 3U by 2. So we get V2 is equal to U by 2. But I know to complete a vertical circle, V2 must be greater than equal to root 5 GL. Therefore, you must be greater than equal to 2 times of root 5 GL, or the minimum speed is 2 into root 5 GL. Make sense? So you still do the same thing, V1, V2, you just will say that V2 should be greater than root 5 GL since you want to say it is completing a vertical circle. Any doubts on this? So you should know the result of the vertical circular motion. Easy? Let's see one more. We have a ball of mass 3m. We have m. We have m. We have m. So let's call them A, B, C. This is D. This guy is coming with speed u. Initially, all are at rest. The ABC are at rest. E is equal to 1 for all collisions. Initially, A, B, C are at rest. Find the final velocity of all the balls. After all possible collisions, what is the final velocity of A, B, C, and D? How do you do this? नहीं रे, नहीं आ रही, नहीं श्रीहरि. Chalo, let me ask you this question. How many collisions are there total? Totally, how many collisions will happen? That is the question. नहीं समझ, after that नहीं आ रही. Chalo, let me tell you one thing. Listen, everyone. So first, A will come and hit A. D will come and hit A. So what will happen? A will start going with some velocity B dash. Agreed? Because A and B have same mass, A will hit B. A will come to rest. B will go with B dash. Then B will hit C. B will come to rest. C will go with V dash. Agreed? But remember, D is still traveling. D does not come to rest. So what will D do? D will come and hit again A. So A will again go with some other velocity V dash. Then A will hit B. So this will go with V dash. Then D is still moving with V3. Now again it will hit A, then again A will go. Are you getting it? D will not stop. So whenever A stops, the D will come again and hit it from the back. Are you getting what is happening? So let's do one thing. Let's find the velocity for the first collision for D and A. Let's do for that. What is the velocity of A and D after the first collision? Let's start from there. Right, Apsa. So if you look at this guy, 3m, let this be v1, and this is m, let this be v2. If you conserve momentum, 3mu is equal to 3m v1 plus m v2. And the restitution E is equal to v2 minus v1 by u minus 0 is equal to 1. So we get v2 minus v1 is equal to u. That's your equation 2. Solve them. So if you take v2 and substitute here, you'll get v1 plus u. So you will end up with v1 is equal to u by 2. And v2 will be 3u by 2. So let's try to read this like this. So after every collision, right, the 3m ka speed becomes half. After collision, Vd becomes half. Right, and Va becomes 3 by 2 times of Vd. Meaning, if this is u by 2, this is 3u by 2. This will help you. So after every collision, d ka speed becomes half, and every time a ka speed will be 3 by 2 times of whatever d ka speed. Now see. This is 3m, m, m, m. So first, these two will collide. You're going with u. This is at rest. So this is your first collision between m and 3m. So after the collision, this guy will become u by 2. This guy will become 3u by 2. Remember, this is 0, this is 0. Second collision will be between these two. Now, technically speaking, all these collisions will happen like very fast, instantaneously, but let's assume there's a small time delay. So remember, 3m is still going with u by 2. In this process, A has come to rest. Now B started going with 3u by 2 because they're the same masses. C is still at rest. The third collision will happen between B and C. Like I said, technically everything will happen at the same time, but I'm just showing you ignoring it. So A and B will come to rest. C will go with 3u by 2. C is gone. Then these two will collide again. This is your fourth collision. So this 3m will not keep quiet. The moment A stops, it will come from the back and it will hit it. Now, just now I wrote a statement. Every time the m collides, what will happen to your speed? Your speed becomes half. So that is the thing. So there is no need to solve 10 times. And this speed will become 3u by 4. So whatever is the speed of D, uska 3 by 2 times. 3u by u by 4. So this becomes 3 times. Sorry, this is 3 times. Yeah. So 3u by 4. This b is at rest. C is going, C is still moving with 3u by 2. So that is gone. These two will collide. This is the fifth collision. This guy is coming with u by 4. This m will come to rest again. This guy will go with 3u by 4. Now look at this. B and C. C is faster, 3u by 2. So B and C will never collide again. Then the sixth collision happen again between this. In total, there are 6 collisions. Finally, 3m ka speed becomes u by 8. A ka speed becomes 3u by 8, which is greater than u by 8. So 3m and m will not collide anymore. B ka speed becomes 3u by 4, which is greater than A ka speed. So A and B will not collide anymore. C ka speed is 3u by 2, which is greater than B ka speed. So B and C will not collide anymore. This is your final velocities. Is that making sense? So in total, 6 collisions. So if you just do this one time, you can just keep using the result continuously. See, u is a variable. Every time it just keeps becoming half. So is this making sense, everyone? Since C ka speed is the maximum, it will not meet anyone. B ka speed is next, and then A, and then D. So after this, there are no more collisions. They will separate out. Sure with this. Any doubts on this? Got this? Let's see one more. Arya, can you keep your cam on?
So can you go to the last slide for a minute?
क्या हुआ रे Arya? There is some problem क्या? You're serious or eating something secretly. You don't want to show it to us. Keep your cam on, na. This is the second time I'm already telling you. Doesn't feel good. It feels like you're hiding something. Yeah, you're hiding a cake. I can see it on your lips. There is a lot of cream and everything. Anyways, we have people secretly eating cakes. Next thing. I'm just joking. Next one. Your seniors were having fun. First, NTA said there is a calculator, then the next day they said there is no calculator. They're crying. You should see them. Huh? They're so happy for that day, actually. Oh, calculator is there. There's no need to calculate everything. Because recently I taught them a certain chapter where numbers are hopeless. Very bad numbers. Matlab, look at the calculations. Huh?
It's mostly physical chemistry where
ये
calculation
होता है ना
helps.
ये भी numbers देगी यहाँ पे 26 into 1.00783 1.00869 55.93493 ये numbers 5 decimals का numbers you have to calculate, you can't approximate this. There is an advanced paragraph on this, so your seniors become very happy like, oh, we can use calci for this. Then next day says there is a typo error, we are sorry. So anyway, they're all scared now. Let's see the next one. 3m. Let's say this is going with you. I'll keep the number same. Find final velocities. This you already know. Find the maximum deformation energy. This is different. Approximately plot kinetic energy versus time graph. And if you ask a statement, is kinetic energy of the system conserved? Just give me the weak answer. Na? First का answer तो already पता है ना? U by 2, 3U by 2. We already did. So let's get the second part directly. First part though, we just did that one. So I'm more interested in BCD. I could have given some other numbers actually, 2M or M, but yeah. Calculations anyway you can handle. What is the catch? How do you find maximum deformation energy? So let me ask you this, forget about that. Can you tell me the answer for D? Is the kinetic energy system conserved, true or false? E is equal to 1, it's a perfect elastic collision. Is the kinetic energy conserved, yes or no? Nope, it is not conserved. So no, you guys are doing a mistake there. If you go back to the story again, what was the story? So this 3M is going with speed U. This is M, this is at rest. And then they collide. When they collide, there'll be some deformation. Okay? And not some maximum deformation. Remember, every collision will undergo maximum deformation. So this is 3M and M. That means momentarily for some time, they both will acquire common velocity. This is like the maximum compression in the Sprinker scenario. And after this, because it's a perfect elastic collision, they will separate out. You will gain back all the energy in this process. This will become V1 and this will become V2. So in this process, you have maximum deformation energy. Your kinetic energy is not constant. Your kinetic energy initially, kinetic energy finally is equal, but not in the middle. During the collision, kinetic energy is not constant. Total energy is constant. What is the total energy? Deformation plus kinetic is constant. Are you getting it? So if you take between state 1 and state 2, this is state 1, this is state 2. We already know these velocities, which is u by 2 and 3u by 2. That we're not interested. So if I do between state 1 and state 2, look at this. Conservation of momentum, 3mu is equal to 3m plus m, v common. So v common will be 3u by 4. So what was the initial energy? Energy in state 1 is equal to energy in state 2. Total energy is conserved, which is half 3m u square plus half 4m v common square. The remaining energy is your deformation energy. So sum of the energy goes into the spring. It's like a spring basically. This is your max deformation energy. So when you calculate this, max deformation energy is 3mu square by 2 minus 2m v common square, which is 9u square by 16. That will be 9 3 by 2 minus 9 by 8 multiply 4 4. That will be 12 minus 9 3mu square by 8. This much energy goes into the thing. And during this process, this is your minimum kinetic energy. So the kinetic energy actually becomes minimum there. Right? So the kinetic energy minimum is how much? The kinetic energy minimum is 9mu square by 8. So if you actually try to plot the graph, kinetic energy versus time approximately. So this was that initial energy. So as the collision starts, your body starts getting deformed, your energy will decrease, and then again you will recover and come back to the normal. This is your KE minimum. Kinetic energy is not constant, it decreases. So this will be a statement question in the exam. In a perfectly elastic collision, kinetic energy initially is equal to kinetic energy finally. That is true. Kinetic energy is not constant throughout the collision. So if I say during the collision kinetic energy is conserved, it is wrong. It is not conserved. In a perfectly elastic collision, kinetic energy initial is equal to kinetic energy final. This is true. But kinetic energy is not constant throughout the collision. It decreases and increases. Suppose if Eka value is not 1, let's say if Eka value is less than 1, the graph will look something like this, which can be calculated. This was the initial value. So the kinetic energy will decrease, maximum deformation, then it will increase and it will become constant. It will not reach the maximum value. Getting it? So this is the case where E is less than 1. If suppose E is equal to 0, then your graph will look like this. The kinetic energy will decrease and become constant. It will not recover at all. You're getting how the kinetic energy graph will change? So if E is less than 1 but greater than 0, it will recover a bit. E is equal to 1, you come back to the same level. This is only for the kinetic energy graph. The total energy will be kinetic plus deformation, if you count deformation as an energy stored. So that will remain constant. All clear with this? So be careful with the word. I didn't say total energy is conserved. Kinetic energy is not conserved. This is the reason you should know the story. What happens during the collision? If you just blindly remember initial, final, and do, you miss that whole point. You will get trapped. You will get some pretty good questions based on this, the collision thing and what is happening in the process. Clear? Let's see one more. Let's say we have a wall here. The wall is going with constant speed v. It's moving with constant velocity. That word is important. And let's say you have a ball here which is coming with speed u, and coefficient restriction is e. Find the velocity of the ball after collision. It's like cycle hitting a train. Train ka speed won't change. I'll tell you one thing here, say. generally after collision, velocity should change. It doesn't matter. Even if an ant goes and hits a train, the velocity should change, maybe in nanometers or something, but it should change technically because there is a force. But here you are saying the body is going with constant velocity. So this words you will keep hearing a lot. If they say the vehicle ka velocity is not changing, the wall ka speed is not changing, that means there's an external force. Therefore, to maintain the velocity, there must be an external force. Now, we don't know that. There must be an external force. How much we don't know, who is applying, we don't know. An external force is applied. That is the reason your velocity is not changing. But if you apply external force, momentum cannot be conserved. So keep this thing in mind. Whenever they say the word something is going with constant velocity, discussion closed, it is gone. Matlab, you can't conserve momentum if there is a collision. How to solve collision problems? We had only 2 points, right? Momentum and restitution. Momentum is gone. So what is left? Only restitution. So use it. V into 1 plus E minus U. I think you're messing up the signs. Ne samyak. Siddesh, right. Are you getting why momentum can't be conserved? No matter how big the wall is, when they collide, the wall velocity should change a little. But if you say it is constant, meaning someone is maintaining that speed, there is an external force. You can't conserve linear momentum. Near Arya, E ray, I didn't give E is equal to 1. Restitution is E only. Give me your answer in terms of E. नहीं आ रहा. Right हो गया. Let's see. Step 1, draw the final picture. This is before collision. After collision, your wall will continue with the same speed. It is given in the question. And this guy, let him go with the speed v dash. Okay. So let's define them. U1. So here U1 is U. U2 is minus V. So here V1 is minus V dash and V2 is also minus V. Right positive, left negative. So E is equal to V2 bar minus V1 bar. You have to substitute here with your velocity, the signs. U1 bar minus U2 bar. So V2 is minus V. V1 is minus of minus V dash. U1 is U. U2 is minus V. So from here you get V dash is equal to E into U plus V plus V. Check.
So we can think about this easily using relative motion.
But then whatever you get will be with respect to this. वो भी कर सकते हो. That is what I'm going to say next. But uske liye na, you should know this result, so then it will become faster. Now imagine if the wall was fixed. Let's say the wall is not moving. If wall is fixed, then you get V is 0. That means V dash will be EU. This is a good result to remember. Huh? Means if you keep the wall at rest, if a ball hits you with a speed U, after a collision, the ball will bounce back with EU. It's a pretty easy result to remember. Clear with that? So if you hit a ball with speed U, after collision, it will bounce back with EU. So now you can do what Arya is saying. If you stop the wall and if you can use the result, then it will become pretty easy to solve. If you stop the wall, the wall will think ball is coming with U plus V. So it will bounce back with E times U plus V. But this is with respect to the wall to add plus V. So, but okay. Clear with this? Any doubts on this? So whenever you hit a wall with speed, you bounce back with EU. Got it. Let's see one more. We have done this in kinematics. A ball is projected with speed U. quotient restitution is E. So this guy will go up, come back, hit the ground, but you won't get the same speed. So we'll again hit the ground, again hit the ground, again hit the ground, and so on. Yeah? So every time it hits the ground, what will be the speed? Second time when you hit, the speed becomes EU. Third time your speed becomes E square U, and so on. The speed becomes in that ratio. Find the average speed. What is the average speed? Total distance by total time. In case you guys forgot, S is equal to A plus AR power 1 plus AR square, so on till infinity. Infinite GP. The formula is A by 1 minus R for R less than 1. This we did in kinematics. Where do we do this? Here, this question. Yeah, the particle is projected vertically with the ground. The speed becomes 5 by 6. So basically, I'm giving you E is equal to 5 by 6 indirectly. Finish off. Last one for the day. This is the third time you're seeing actually. First time you saw this thing in Infinite GP in the foundation course. If you guys remember, we did this thing in foundation. There. Ball is dropped from height is find the total distance. Then we saw in kinematics. This is the third time you're seeing. Answer will come in terms of U and E. Find the average speed, which is the total distance by total time. Right, Ishma, you got it. Try others. I'll give you a minute. Get this thing. I'll get some water and come. Let's see who else got the answer. नहीं उत्साह 22 कैसा आया रे? ये क्या वैल्यू दिया ही नहीं मैंने. Right, Samyak. Right, Siddesh. Right, Anvita. Aditi, yeah, you got it right, Aditi. Let's see. So first time when you go with speed U, you go up and you come down. So here H max will be U square by 2G. Time of flight is 2U by G. Second time your speed becomes EU. And you can clearly see H is proportional to U square and time is proportional to U. So in the first case, if the distance is H and H and the time is T. Second case, the distance will be E square H, and the time will be ET. The third time it will be, you can see this thing, they're forming a sequence now. This will be e power 4h, e power 4h. So it will be e square ka thing, and this will be e square t, and so on. So average speed will be total distance by total time. The total distance will be 2h plus 2 times e square h plus 2 times e power 4h, and so on till infinity, by time will be t plus et plus e square t, so on till infinity. Take out 2h common and take out t common. You end up with 1 plus e square plus e power 4, so on till infinity, by 1 plus e square, so on till infinity. There are two infinite GPs. H will be u square by 2g. This will be 2u by g. The numerator will be 1 by 1 minus e square. Denominator will be 1 by 1 minus e. Makes sense? Because r is e and is this thing there. So that will become 1 plus e. This is a g will cancel, 1, 2 will cancel. You end up with u by 2 into 1 plus e. Check. One minus e square can be written as 1 plus e into 1 minus e. So 1 minus e will cancel off. Check. That's your average speed. All clear with this? That's a bit about this thing. So next class when we catch up, we'll continue from here. We will do maybe 1 or 2 more head-on problems, and then we will go ahead with oblique collisions. So collisions, basically that only. If you know how to conserve momentum and restitution, you'll be able to handle most of it. And then next week we will do more collision problems in the next class. And then I think mostly by next week we should be able to wrap up this chapter. Next Tuesday we'll wrap up the chapter. After that we'll do variable mass system, rocket propulsion, and all that stuff. That should, I think, another 2 classes we will wrap up the chapter mostly. And then we'll start off with rotational mechanics. Okay, with that we'll wrap up for the day. So please make sure to go through the notes. We already did almost 42 problems, right? So you can start solving. Actually, if you're solving HCV or if you're solving your material, you can start doing, questions, center of mass, momentum, head-on collisions that you can handle. After next class, you'll be able to handle everything. Okay, with that we'll wrap up for the day. And do remember, there's a test online till Thursday or Friday. Check out the deadline I posted in the group. So accordingly to that. Okay, those routes can stay back. Others are free to leave. I'll see you on again Thursday, same time. So take care, stay safe.